REALISM, short for Realistic Simulation of Materials, is a Houdini plugin that helps animators and technical artists easily simulate the behavior of various materials. This is our final project for the course CS660, Advanced Topics in Computer Graphics. On the right is one rendered image of our simulation of sand in an hourglass. As the computing power grows, animators and artists would like to simulate materials, not only in a visually pleasing way, but also in a physically correct way. It is also important to simulate its effects with high performance so that people can get instant feedback. So our goal is to design a high-performance solver for animators and technical artists to simulate multiple kinds of materials in a realistic way. We've decided to implement a Houdini plugin with an easy-to-use interface. Under a small number of particles, our plugin can achieve a near real-time performance. We have three built-in material types: hyperelastic, snow, and sand. For each of the materials, we have a preset of physical parameters, but the users are free to modify these parameters according to their needs. Users can use arbitrary geometries for both material shape and collision objects. In order to improve the authorizability of our plugin, we also implemented the feature to set separate start frame and initial velocity of each input geometry, which will be explained in detail later. The main algorithm we used in our plugin is called Material Point Method, or MPM. There are many papers that discuss different variants of this algorithm. For our plugin, we mainly refer to the paper A Material Point Method for Simulation from SIGGRAPH 2013 and Drucker-Prager Elastoplasticity for Sand Animation from SIGGRAPH 2016. On the right is a flowchart from the first paper that shows how this algorithm works from a high level. Material point method is a method that mixes both the Lagrangian and Eulerian point of views in fluid dynamics. This allows us to take advantage from both sides. We can use a pseudo-algorithm to describe the method. At the start of the loop, we transfer the physical properties from the particle domain to the grid view, for example, mass and velocity, and on the grid, we can use discretized formulas to calculate the forces on each grid point. Once we have the forces, we can update the velocities at grid points. At this step, we also take into consideration the presence of collision objects. And finally, we transfer these properties back into the particle domain and start a new loop. Next, we'll show a typical workflow of our plugin. For example, if we want to simulate a solid sphere in Houdini, we first add an NPM source node to the network and connect our geometry to the source node. In the source node, we can edit parameters such as point separation, initial velocity, and particle mass, and so on. If we choose to view the source node, we can see that our solid sphere has been voxelized into particles. Next, we insert an NPM solver node to the network. This solver node takes in two inputs. The left one is the geometry, which is the NPM source node we created before, and the right one is the collision object. In this example, we use a box as our collision object. In the solver node, we can edit more parameters, such as Young's modulus, type of the material, type of the collision, and friction coefficient. After everything has been set up, we can start simulating the material by clicking the play button. This short clip demonstrates the effect of initial velocity and starting frame. As we can see, both objects have an initial velocity towards the right, but the yellow cube has a non-zero starting frame,
so it acts like it's always chasing the cube.
We have set up several things to demonstrate the feature of our plugin.
Due to the time limit, we didn't render the whole scene. The scene setup is shown in the upper right image.